Good morning, grade 10. This is chapter 17. It talks about Newton's laws. First of all, we have to remember that two of the most important quantities in physics are force and acceleration. I'm sure you know both of them. We have seen them in the previous chapters. So acceleration is the rate at which the velocity changes with time, and force is quite simply a push or a pull. So these are the most important quantities in physics, and we will need them in this chapter. Now, Newton's laws, it's divided into two parts: Newton's three laws of motion and Newton's law of universal gravitation. Newton's first law of motion. This law states that objects don't start or stop moving on their own. This observation is the essence of Newton's first law of motion. An object at rest remains at rest as long as no net force acts on it, and an object moving with a constant velocity continues to move with the same speed and in the same direction as long as no net force acts on it. So in both cases, I don't have a net force. So whenever I don't have a net force, the object that is at rest will remain at rest, and the object that is moving with a constant velocity will continue to move with the same speed or velocity. When you sit in a chair, there are essentially two forces acting on you: the upward push of the chair and the downward pull of gravity. Since you are at rest, the two forces must cancel out. Therefore, the vector sum of the forces or net force acting on you is equal to 0. So whenever you have something that is standing still, it means the net force acting on this object is equal to 0. When placed at rest on a level track, the cart will remain at rest until given a push. And in accordance with Newton's first law, once the cart is in motion, it will remain in motion until acted on by a net force. In theory, if the track could be made infinitely long and perfectly frictionless, the cart would continue moving with a constant velocity forever. So theoretically, every object should keep on moving with a constant velocity, but this doesn't happen. We will see why. Newton's first law is sometimes referred to as the law of inertia. Inertia means the tendency of an object to resist any change in motion. So if the object is at rest, it will stay at rest. If the object is in motion, it will stay in motion. This is why Newton's first law is referred to as the law of inertia. So an object at rest remains at rest, and an object in motion remains in motion at a constant speed and in a straight line unless acted on by an unbalanced force. Examples of Newton's first law of motion. First, car suddenly stops and is strained against the seat belt. Because you have to complete your motion, there is no force acting on you. You have to complete with the same constant speed. But since we have the seat belt, it will hold you back. 2. Car turns left and you appear to slide to the right. In fact, you're not sliding to the right, but since the car changed the direction, it will appear that you are going to the other direction. The difficulty of pushing a car that won't start. This is inertia. The car is at rest and it will stay at rest. It's too hard to move it. Now, things that are still stay still, and things that are moving keep moving with the same speed unless a force of some kind pushes or pulls on them. So an object at rest will remain at rest, just like this ball, unless acted on by an unbalanced force. So when you kick the ball, you are applying a certain force. This is why this object cannot remain at rest. An object in motion will continue with constant speed and direction. So when the ball is moving, it will continue to move, unless acted on by an unbalanced force. When it will reach this net, it will stop. With no outside forces, this object will never move, and with no outside forces, this object will never stop. In the first figure, the object is not moving, and it will not move unless you apply on it a certain force. And in the second figure, the object is moving in the given direction, so with no outside forces, this object will never stop. Examples of Newton's first law of motion. Why was it so difficult to stop the Titanic from colliding with the iceberg? So the mass of the Titanic is very large, so inertia is proportionate to mass. The Titanic could not change its direction because its extremely high inertia forces it to continue in a straight line, thereby colliding with the iceberg. So this is why it couldn't prevent from colliding. Examples of Newton's first law of motion. Okay, don't let this be you, wear seat belts. Because of inertia, objects, including you, resist the change in their motion. When the car is going 80 kilometers per hour and it's stopped by the brick wall, your body keeps moving at 80 kilometers per hour. This is Newton's first law. Your body is resisting the change in motion. This is why it has to complete moving with the same speed, which is 80 kilometers per hour. This is why it's very important to put seat belts. Now, if objects in motion tend to stay in motion, why don't moving objects keep moving forever? This is a very important question, and the answer is things don't keep moving forever because there's almost always an unbalanced force acting upon them. Most of the times it's friction or gravity. So, a box sliding across a table slows down and stops because of the force of the friction. Otherwise, it has to keep on sliding on the table. If you throw a ball upwards, it will eventually slow down and fall because of the force of gravity. Otherwise, it will have to complete its motion upwards. In outer space, away from gravity and any sources of friction, a rocket ship launched with a certain speed and direction would keep going in that same direction and at the same speed forever. So in space, we don't have gravity and we don't have a friction. So if we have a rocket with a constant speed, it will complete the motion. It will continue its motion with the same speed. Now, Newton's second law of motion. This law tells how a force changes an object's motion. So the acceleration of an object depends on the mass of the object and the amount of force applied. An object's acceleration is directly proportional to the force and inversely proportional to the mass, which is A equals F over m. The acceleration equals the force over the mass. So the net force of an object is equal to the product of its mass and acceleration, or F equals ma. This is the same formula, A equals F over m. Newton's second law for a single force, force equals mass times acceleration, F equals ma. In this case, the net force couldn't be equal to 0. If you remember in the first law, in both cases, whether the object is at rest or in motion, the net force should be equal to 0. So the first law is practically concerning objects that have a net force applied on them equals to 0. The second law is when the net force is different than 0. What does F equals ma mean? Force is directly proportional to mass and acceleration. Imagine a ball of a certain mass moving at a certain acceleration. So this ball has a certain force. There must be a force applied on this ball in order for it to be able to move with a certain acceleration. Now imagine we make the ball twice as big, which means we double the mass, but we keep the acceleration constant. If you want to keep the acceleration constant, F equals ma says that this new ball has twice the force of the old ball. If you replace the new m by 2 of the oldest m, you'll get F equals 2ma, which is 2 times the previous F. So if the object is bigger, the force should be bigger in order to keep the same acceleration. Now imagine the original ball moving at twice the original acceleration. Now I want to double the acceleration. F equals ma says that the ball will again have twice the force of the ball at the original acceleration. So we have a new acceleration which is equal to twice the acceleration in the beginning. The new force applied should be twice the force, the original force. F equals ma means that the force of an object comes from its mass and its acceleration. Something very massive high mass that's changing speed very slowly, low acceleration, like a glacier, can still have great force. Something very small, low mass, that's changing speed very quickly, high acceleration, like a bullet, can still have a great force. Something very small, changing speed very slowly, will have a very weak force. So it's not only about mass, it's about acceleration. If you want a high force, you either have to have a big mass or a high acceleration. Examples of Newton's second law. Hitting a softball, the harder you hit, the faster the ball goes. Why? Because the harder you hit, it means you are applying a biggest force. The faster the ball goes, when you apply a biggest force and you have the same mass, which is the softball, the acceleration should be bigger. So the harder the hit, the faster the ball goes. 2. Football players and their positions. And 3. Loaded versus unloaded truck. So whenever you want to move a loaded truck or an unloaded truck, it all depends on its mass. One rock weighs 5 newtons, the other rock weighs 0.5 newtons. How much more force will be required to accelerate the first rock at the same rate as the second rock? So I have 2 rocks and I want them to have both the same acceleration. So how much more force will be required to accelerate the first rock at the same rate as the second rock? 10 times as much. You need the same A, so A is constant. A equals F over M, so you have the first F over 5 newtons, the second F over 0.5 newtons, and the difference between them is 10 more times. And that's the end of the first part of this chapter. We are going to complete the chapter in the next video.